It's in progress. Share screen. Set. So just put that guy here or something. All right. So let's see. We'll see how this works. Anyway, so I'm recording that. It's all set up. Okay, the homework. So I'll just go through the homework today. So it's about this. There's a paper. Let's see, plus. All right, so this paper, so it's viscosity enhancement. So he's got, this is a picture. So you have the viscosity of motor oil is what he's talking about. So like synthetic oil versus regular oil, and then all the additives they put in normal oil too. So idea is like your engine gets hot and then like the viscosity drops. So then the oil, if you have an old car, like leaks out into the cylinder and you burn the oil, or it's not good if you don't have like constant viscosity. That's the idea. So somehow you want to level off this. And this guy's fallen with this. So it's going to fall with the uranium spectrum. So expect viscosity to go with some zero viscosity and exponential of some activation energy over KT. And if you plot that, and one way to plot it would be like log, would be like linear over T. So normally you plot like log is something versus 1 over T. That's called a Arrhenius plot. You expect to see a negative slope. This is the energy of activation. So that's an Arrhenius plot. It can be anything here. Chemical reaction rate, any kind of rate or time, like tau, could be some kind of time-dependent thing, and then the temperature means that the original idea was from viscosity. So you had like this stuff, right? And then your magic one here, the red one, is going to have to go here. Right? So that's kind of like flow. That would be like the simplest flow. It means like this guy has to move there, it has to move there. So there's, if you plot the energy versus the reaction coordinate, then there's this peak in it, and that's the activation energy. It's like where it has to be here to move the stuff out of the way. Okay, so you can measure that. And temperatures moving everything around. Everything's like KT motion. So the higher the temperature, the easier it will be for it to get through that barrier. That's kind of the concept behind this gut function, this plot. Right? So plot that linearly. If you plot that, then it looks like that. Okay, so this is like chemical engineers always try to linearize equations. This is how you linearize that equation. And so then this is what it looks like in reality. It means you have like a huge drop in viscosity. It's just gonna take a dive. So, and that's not good for your motor. Right? So you can add stuff to it. One thing you can add is this polymer that undergoes a phase transition. Okay, so I go back over there. So there's kind of two, for simple systems, it's like two kinds of phase transition. The normal kind is like salt and water or sugar and water. Then you have like temperature and composition of salt. And then you have something like this. Like, it'll be skewed because on one end you have salt and the other end water, like percent salt, like NaCl. There's some critical point. This is two phase. So as you cool it down, it phase separates. But if you go to infinite dilution, it never phase separates. The same thing if you have, so that'd be like pure salt. That'd be pure water, sorry. This is pure salt. So pure salt with a little bit of water also never phase separates because it just hydrates the salt. And over here, pure water with just a little bit of salt will never phase separate either. This has to be like infinitely dilute or infinitely miscible, infinitely miscible in this a place where it's, so it has to be like a U-shaped thing, right? Just by logic, because you have some place where it does phase separate. So this is called the critical temperature, right? And you could also have a critical pressure, critical density of composition, right? So that's a critical point. So generally, I mean, in thermodynamics, talk about later on, like critical points are places where everything like stops. Like it's not a good place to be in terms of predicting what's going to happen, because at that point, the water, the salt's just as happy phase separating out as it is being in solution. So you can't decide like where it wants to be. So if you plotted like the free energy versus composition, and you looked at that critical, so you did curves for different temperatures. It's some free energy, some function and temperature. You'd find out that the free energy is flat there. And then you find out that in the single phase region, the free energy will look like this. Like so, if you have some composition that tries to phase separate, it's a steeper drop. So both sides drop. Let's see, get that wrong. It'll be like this. Sorry. So both sides go up. That means it wants to lower the free energy, so it'll just stay at the state where you are, the composition where you are. When you get to the two-phase region, then it's got like this kind of shape. So if you're in this region, which would be this region, the composition, then it'll be like this temperature. So this is T2 or something. Then you have 2 points of criticality. Those are like your 2 binaural points. Right? So any place in here, it's going to have like more down than up, so it'll phase separate. So any place within that kind of frown face part gives you phase separation. Any place where it's like smiley face gives you one phase. It's kind of the rule for the free energy plot. Right? So anyway, so this thing is at the top because so that's called a upper CST, critical solution temperature. So it's called a UCST system. So those are rare in polymers. It's, for everything else in the world, that's the way things happen. You cool down and phase separate. So you want to wash up gunk from the counter, use hot water. You don't use cold water, right? Or hot whatever, ethanol, anything. Right? So it dissolves when it's heated up. Polymers, on the other hand, generally the cold water is a better bet. And hot water will make it phase separate. So the hotter you make the water, the gooier the counter gets. So you go in with cold water, it wipes right up. Okay, so it's kind of a strange thing because this thing's all governed because you have temperature, temperature times entropy and then free energy. So it means entropy is driving the phase separation. So if you raise the temperature, the free energy goes negative. You randomize it more, it mixes. If enthalpy, on the other hand, governs it, so things are like that. There's a lot of randomness, but if you glue them together, there's no randomness anymore. So the entropy goes to 0. Then you just have this enthalpy term. And enthalpy can have like you said, water. So if you have positive charge and you have water organizes around it, so that's an enthalpic interaction, but it's got an entropic part to it. So it's got a temperature dependent part. So there's this enthalpy part, like a normal enthalpy that's positive, and this organizational part that's negative. And basically this thing, these bonds will break apart at higher temperatures, so it becomes, it becomes less miscible at higher temperature for some reason based on that. We'll talk about it later, but basically, in that case, when you heat it up, it phase separates. You have lower critical solution temperature, LCST. Same behavior, it has a critical point, same free energy thing, it's just upside down. So it phase separates when you heat it. Some systems can have both UCST and LCST, and some systems can have like a window of miscibility, like that, where they use something. Anyway, they can have a window of miscibility and everything else is not miscible. And there's probably some other cases. right? But basically, the normal one is this UCST, and then the oddball one is this LCST, but that's normal for polymers. For instance, polyethylene oxide, which is like this guy. So it's poly glycol or polyethylene oxide is like the most popular water soluble polymer, right? Because it's industrially produced somehow petrochemically. And anyway, so that guy has a phase separation temperature of 60 degrees C in water, right? When you heat it up, and it's an LCST. And almost everything, like in this paper, they're using a thing called tween 10 or something. So these are non-ionic surfactants, which are usually PEO and like PPO or some other group that's oleophilic. So hydrophilic, oleophilic, that you make things like surfactants that don't have ionic charge to them. And you can make a lot of things with them. Anyway, so let's see. Right, so yeah, there's a lot, and this is only a small part of what's in this. Like, actually, I realized like to do this whole paper would be a lot. So I think it's like between 10 or something. Let's see. What does he use in here? I wrote it here. I don't know, somewhere, but he says in the how to make the samples part. Materials and methods. Or I could just go find. Tween's like a 23 tweens. Huh? Between. All of them are between. I spelled it wrong. Where's that one? It's a lot of, this guy likes to use the word between. All right, well, let's see it. Okay. Non-ionic detergent. So we don't have the wiki page for it though. There's a picture of it. Tween 20. I think it's tween 20. So it's got, see these groups, the CCO to the Z, CCO to the Y, CCO to the X. So those are polyethylene oxide. It's got a hydroxyl N group, and it's got this norbornene or something connecting unit, and then it's got a fatty acid stuck to it. That's hydrophobic. That's oleophilic. So it's oil, water. It's got this weird structure, but it'll always be like PEO stuck to something that's hydrophobic. Could be PPO, could be fatty acid. So there's a bunch of these. There's a bunch of these tweens. Like there's a whole family of them, and then there's a bunch of other non-ionic surfactants, but they're all going to be like the same thing. PEO stuck to something, and they all are going to have a roughly 60 degrees C. Phase separation point is an LCST, phase separates on heating, right? It means whenever you're using these things, so here he's taken that, oh, wait, that's why, this is the wrong paper. There's two papers here. Shoot. That is this paper. This is the paper where he has tween. He has like a, it's the same as last week. He's got an oil and he's got a non-ionic surfactant. Then he's got a PEO chain and then polystyrene. The polystyrene goes into the hexane phase, but that's got a UCST. Then the PEO has an LCST. So it's got both phase separation types in it. This is a question E. Sorry, this guy got him mixed up. This guy. What is this guy? This guy doesn't have tween in it. That's why you can only find between. But this guy just has these polymers that are polymethyl methacrylate, which is, so the double bond here polymerizes. So this is the vinyl group. And then you have a methyl group stuck off, and then you have this kind of carboxylic group with a methyl on it. Right? That's PMMA, like plexiglass. Right? 1930 something, isn't that? Right? And this is PMMA with 16 carbons on it. It's like a fatty acid almost stuck to it. Right? It turns out with that, you can get, so PMMA, I guess, just goes into oil, no problem, never phase separates. And then if you stick this thing on it, it has an LCS, it has a UCSD, so phase separates on cooling. So that means if you cool the thing, so the coil, the idea is like, so it's not like a novel idea, you know, but basically, so if you, let's see, so you have your coil, expanded coil, right? And we have DF is 1.67. That's our Florida creep down rule, right? Then there's a theta coil, fractal dimensions 2. And it's like a collapsed fractal dimensions 3. Hopefully you don't see that because these are the ones. So he wants to go between those two transitions. And then, so this is going to happen when it's soluble, so when it's hot. And this is going to happen when it's insoluble, so when it's cool. And the viscosity is going to go as the solvent viscosity times 1 plus some number times the concentration of the things that are going in. And this number has to do with the size of the thing. R cubed. In fact, this is going to be like the 1 over the overlap concentration. So it's going to be the mass of the thing by R cubed. That's how that thing will behave. So if R cubed goes up, then this concentration and the viscosity goes up when it's hot. And then when it's cold and it collapses, this number goes down. And then that, so this is called the Einstein equation or something of viscosity. This thing for spheres, for 3D spheres, this thing's 2.5. And for polymers, it's going to follow this rule. Okay, so remember, M goes with size to the fractal dimension. You have two different fractal dimensions. You have R to the 3 minus DF, minus 1 over DF. So it's R to the 3, and then M will be, M is 1 over DF equals, oops, no, R to the DF, sorry, 3 minus DF. Okay. So when it reaches 3D, this thing goes to 0, and this thing's a fixed number 2.5. The dimension's 2, this is 1, goes with R. And then if it's 1.67, some other higher power of R, so it's a bigger number. And so anyway, so that's how this thing works. Like that's what he's talking about in this paper. So you're doing this transition. So what's he going to do? He's going to do the solution viscosity measurement. He's going to do a dynamic light scattering where he gets this hydrodynamic radius, so equivalent sphere in terms of flow. So you have like the friction factor is going to be this RH 6 pi times the solution viscosity, Stokes law. So you can measure, you can get this hydrodynamic radius, equivalent sphere radius in terms of flow. So he does that measurement, and then he's going to do a neutron scattering where he tags this chain, or he takes a solvent, deuterated, and he just sticks his stuff in, and he runs through the temperature cycle to see what happens to it. So what do you expect to happen? Like, all right, so basically, let's see. There's a lot to this paper. Let's see. I want to go back to the PowerPoint guy. Slides 2 or something here. Here we go. Back up. All right, and then let's see. This is projected, or yeah. All right. All right. So so we had this plot. Right? There's a bigger picture over here. I guess that's not bigger, but as you go through temperature, so this is the theta temperature. So we said that we had, let's see, not this, not that. So this is after this. Here, this thing. So he said, like, if we're at this magic, so chi is 1 by temperature. So if we have this magic temperature, 1/2 chi can be 1/2, and this thing goes to 0. We just have the Gaussian chain, the one that's smaller. And then as chi gets larger, so at higher temperature, chi gets smaller, and then this will be positive, and then we have expansion. So the thing dissolves. So the bigger chi, the more immiscible it is. Right, and then as it gets smaller, let's see, as you raise the temperature, it gets smaller. It becomes miscible. Okay, so that's the idea. So basically, he's messing around with this equation. So we know from this equation, then because we can take the derivative of it, we can solve for R. We can predict a functional form for this R. Right, so we know how the coil size should behave with temperature. Like chi will be 1 over temperature, so it should follow like this curve. The black line is actually that function, right? So basically, the temperature dependence of the coil size under this scheme is known, and it's not going to be a straight line. It isn't like radius versus temperature. It's this curve that follows this equation, whose chi is 1 over t. So this is kind of a complicated functionality. It basically looks like an exponential thing. Actually, it looks like an error function, which is like an integral of an exponential. Right. So anyway, it looks like that. It isn't a straight line. Right. So we kind of know that functionality is here. So we expect to see the guy in the paper like going, oh yeah, and then I can get chi from that curve. Like, in other words, there's only one parameter here. He knows t. He knows the Kuhn-like. B is a Kuhn-like. He knows the molecular weight. Maybe he can figure out all these terms. He knows the Gaussian one because he measures it. So he could get chi, from this. So you think he would just do that, especially because he's from Santa Barbara, which is supposed to be the best materials program in the world. Right. But nonetheless, like, paper is kind of dumb, That's pretty dumb because they don't do that. Like, they don't bother to do that. In fact, what they do, it sounds like some guy from like Phillips Petroleum or less, wrote the paper, because the way they're looking at it is really like pretty. They have nice equipment, but they don't seem to know like what to do with it, So they plot. So they plot the rate gyration versus temperature, and they draw a straight line through it. So that's kind of like dumb. I mean, you wouldn't normally do that. So they have this PMMA mixed polymer in 3 flavors. So one's linear, like the easy one. Then one's like randomly branched. Okay, so this would be like conductivity dimension 1, it's linear. Conductivity dimensions like 1.5, it's randomly branched. Then these star ones that are complicated because in this case, these arms the arms of the polymer correlate with each other. So you assume everything's random here, like mean field. Once they're stuck together, it's not mean field anymore. They can tell the direction where the next arm is. And they tend to like straighten out. So there's a lot of complications, especially stars that are like 8 and 9 arm is a lot. Like a 4-arm star is kind of okay, a 3 arm's okay, but once you get to like a lot of arms, it becomes something a lot more like a dendrimer or something. So dendrimer, so there's a lot of flavors of this kind of thing, because you can do easy, simple, kind of idiot chemistry in this stuff. So you can take silica. So SiO2 is glass, right? If I just make another Si here, but I can put like an organic on here, like methyl. Or I can just put chlorine on here. Right, so SiCl4, that's super reactive. Like, so that if you put it if you put it in with NaOH when you put water glass, it just turns into glass. You change the pH, it makes glass. So water glass is used to make colloidal silica, things like that. So basically, you start with sand. you put it into like HCl or NaOH, and then you get this water glass, which is pH 14. And if you drop the pH, it makes nanoparticle silica. That's how you basically industrially make the stuff, absorbents and things. So, so if you stick ethoxy groups on it, then it's more controlled. It doesn't just like kind of blow up, right? So methoxy, when it reacts, is going to hydrolyze and make ethanol, which makes you go blind. That's the stuff, and the bad stuff in booze that'll like make you go blind. And in fact, it does it by absorption through your eye, not through your body. So basically, if you're just around it, that's how you go blind. So the vapors that get you, right? So methanol is not good to have around. So TMOS, tetramethyl orthosilicate, is kind of like not liked that much, even though it's reactive and it's a good chemical use and functionality. So they put on an ethyl group, TIOS, is like the most popular one. And then that guy, it's going to release ethanol, which is like, drink it, kind of. Still poison, but people, doesn't seem to bother people. So anyway, so you can react that. And if you have a polymer, like say you have PEO with a hydroxyl N group, it'll hook up with the ethanol, just make ethanol. Then you have like a tetramer of PEO, this 4-arm star. And you can do that anywhere in your kitchen. It's really easy to do. It just happens. Then if you can take 2 of these, and then you can have a 6-arm star. Right? You start with a disilonol, and you can do a 6-arm star. You have 3 of them, and you can do whatever you want. So you get any kind of star you want, just starting with this is called condensation reactions. This whole salt gel chemistry. So it's really simple to make these stars, especially of a polymer like PEO that has a hydroxyl group on the end anyway. Right. So it's kind of chemistry. As someone like in elementary school can do this easily with no problem at all. It's just like mix of stuff, stir it, boom, done. You can also make networks with this. Like you can use this to cross-link PDMS, like bathroom caulk sealant stuff. Right, so that's how it's made. So it's like pretty easy chemistry to do. Anyway, so the stars are easy to make. And if they get too many arms, or they're not easy to study. Then you can also have cases where you have another junction, so you make a dendromer. So you have the original thing has 4, and then it's going to have, and then you have like short molecular weight hydroxyl groups put in. So the next one is also going to have 4, and pretty soon you have this kind of tree branch thing, except 4 instead of 3. But that's called a dendromer. And these things called generations. So generation 1, generation 0. Generation 1, generation 2, generation 3, you have a 16 generation dendromer that's like this blob. It's a colloid, really, but they call it a polymer. Right? It's actually a colloid. It's actually a 3D object, really. Right? But it can be used to port things around. And the chemistry, again, is like simple. It's condensation reactions, and then you start with a low molecular weight linker, if you want to make a dendromer. So this kind of stuff people like because any idiot can do it, and there's a lot of idiots. So it's like basically it's kind of fun to do, I guess. And they can do things kind of like what they're doing here, but they just bought their stuff. They didn't make it. Anyway, so that's what this thing is, almost another subject. So anyway, they have. So the only part of this I'm really looking at. So they do viscosity measurements. They get the intrinsic viscosity, that number versus temperature. That's basically measuring the overlap concentration, right? So here we have, I said last time, you have forgotten, they have the chain. These chains are floating around. Each chain is porting with it a concentration, right? So it's got a mass and it's got a volume. So that's some concentration called C star. So if the solution, if C is less than C star, you call it dilute. And if C equals C star, you call it overlap. overlap concentration. If C is bigger than C star, you call it semi-dilute. Right, so at semi-dilute, the things start to entangle. So if you look at the viscosity versus concentration, you reach C star, you expect power 1, like if you do log, you may expect power like 3 point something once you reach C star, where the thing overlaps. So he measures that here. All right, so C star is an important concept to have. And it turns out that that's basically, like I wrote, the intrinsic viscosity is R cubed over M. So it's basically 1 over C star. So this number, so you look at it, if you measure the intrinsic viscosity by measuring the viscosity and then the solvent viscosity. Right, so if I can measure the solvent viscosity, and if you do use Brussel's law, it's the time that it flows through a tube. So you measure the time it takes to flow through a tube for the solvent, then you measure the time through a tube for the solution, and then you take the ratio of the two, so that the prefactor, all the radius and all the Brusel things, pi and whatever, fall out. Then you just get this 1. If you subtract 1 and divide by concentration, then you directly get this C star number. Right. So that's going to be like 1 over C star. So you just get it, and you can just use a stopwatch and a tube. You need kind of a nice uniform tube. It's longer, so that there's no end effects on it, that kind of thing. And because you have viscosity goes with this to the exponential over kT, then basically you have a constant temperature, like a temperature bath, because the viscosity again is going to go like crazy in temperature. So you need to have really constant temperature. Basically, this measurement is also a bathtub kitchen kind of measurement. Not hard to do. You have to keep the temperature constant. So he does that. I mean, there's machines to do it, but basically it's not going to be much better. All right, so he gets that intrinsic viscosity, which isn't viscosity at all. It's 1 over a concentration. Someone says what's the intrinsic viscosity? And you go, it's not a viscosity, it's a concentration. It's 1 over C star. Right, so he's saying 1 over C star, as you increase the temperature, so as the things get larger, C star gets smaller because they get bigger and they can overlap earlier in concentration. Right, so his intrinsic goes up because it's 1 over that. So that's kind of good. I mean, shouldn't be linear, but that's okay. So anyway, so the scattering part though is kind of interesting. So he's got, because then we can look at like this dimensional business of coils expanding and shrinking. Here, this copolymer, so it's a random copolymer. So it's just a mixture. He shows in the picture. It's a random mixture. I think the gray ones have the tails and the black ones don't. So the black ones are plexiglass. The other ones are plexiglass with an oil stuck to it. And it's random, like randomly placed along here. Right. So linear, branched, and then star. Right. So he's got 3. And then he does the neutron scattering. So you think, well, there's not much you can do because he gives these like tiny little plots. So that's where I wanted to bring this Igor thing in. So if I can do this. I'm wondering if this is going to go to the to the thing on Zoom, but hopefully we'll find out. Anyway, it's big there and it's really small here. It's kind of weird. So anyway, this thing, I sent you this experiment, called an Igor experiment. So it's like the thing, and it's got like a linear code. You can say like, and it'll beep for me. So you can just put this, it'll just interpret whatever you type in. And it's also got like a menu driven thing. So it's a big program, but you can stick in, this include means it's including some code inside this procedure window. An Igor thief is a code you can include, right? And that thing is like, you can digitize the plot. So you go, see, I should have this already open here. So you can play around with this. The only part, you're not going to need to use this, but So it explains how to use it. To use that, you go under data packages. It tells you how to do it once you have it open. And it goes there. I had one open, but I'm not sure where it goes to when it does that. But this is a program someone wrote, but I have like the linear. So you can get that's just like clipped from the that paper, and you can clip it in here. Then you set your like XYZ, and then you just click the boxes and you digitize the data. So I did that already. I did it for all of them. You can play around with it if you want, but it's pretty useful to figure out where people are lying to you. Because they'll plot this, like you can see, instead of doing this plot, right? So he's going to get the radius of gyration. So you have like the intensity goes with some I naught, and then exponential minus and the Gaussian Q squared, and some constant times Q squared. So this thing's a bell-shaped curve that gives you the radius of gyration. You fit the data. So you're only looking at half of the data. And if you do log I, log Q, that's kind of what you can use now. There's some power law like -2, right? That's df. So anyway, so instead of this, he takes like log of I versus Q squared, which linearizes that equation. And then you get a straight line from the slope, you get RG squared over 3. Right, so that's what he does in the paper. But this plot is really confusing. Like you can't tell. Because if I take the power law and I put it on that, it also is a straight line. Like anything that's like log is going to kind of look like a straight line. So basically, in fact, for power 2, it'll be a straight line because we have I scales with Q squared. Anyway, you can, if you take a narrow enough range, it's going to look like a straight line. It isn't a raised gyration. And you have to see that it's a bell-shaped curve to say you're using that rule, right? So in that plot, you can't do it. So that's called a Guinea plot. But anyway, so I digitized all this stuff and get rid of that. You can play around with that if you want. It's useful to kind of mess around with things. But and I replotted them, and I made like even decades here, so it's easy to see. Make this bigger from me, so it's easier to see the power laws. You have. You can't see it. All right, so let me put it up. Sorry, this works. So, all right. Did you not see anything I did with Igor Thief? You saw that? Oh, yeah. Okay, all right, good. So this is power 1 because you have 1 decade or 1 decade. Right. And then this guy, this is power 2. It's like 2 decades by 1 decade. And then this is power 1.5, 1.67. Like it's a little bit more than a half. So actually I just drew that. So that matches pretty good. That's nice. That means you have expanded coil, which you kind of want here. Right. And then this is power 4. Okay, so power 4, and there's only 3 decades, so you can't see the other half, but that's power 4, and that's kind of happening out here. Okay, so power 4 means that you have basically that's Perod's law. And it's basically the intensity goes with the surface to volume ratio times Q minus 4. That's oops. Huh? Oh, sorry. I thought I just did this wrong thing. All right, so you have some solid object that's got a surface. So you're talking about binary interference. So like binary here, the 2 things are the same, so that equals 0. Binary in here, the 2 things are the same, so that equals 0. The only place you contrast is at the surface for a solid object. So basically, until you get to sizes where you can kind of cross the object and you have the radius of gyration. So for solid objects, you get this Q to the minus 4. The prefect is the surface area, which is the only place where you can see anything. Right. So you're looking at powers of -1, -3/5, -2, -4. This is solid Gaussian expanded coil rod. Those are kind of the things you're expecting. So you draw a line for that, try to find it in the plot. All right, so anyway, this is his curves for the linear with the 4 temperatures. So he has this line. that's expanded coil, and it's in all of them pretty much. Right. And then there's a transition to this tube out here. And that transition point, so for this, the red is 25, so that's cold. It should be the that's starting to phase separate. And then the blue is here, so that's also got a transition point. Then the green and orange is 90, and the transition point for 90 is way out here. So this is a 2, right? Yeah. So for the 90, it's like here. For the 25, it's there. So higher Q means smaller size. Okay, so from this data, ignoring the 4 part, which is kind of weird, the transition shifts to smaller size as you go to higher temperature. Right. So this is the reason, like why. Let's see. Why you get this curve. In other words, this thing explains the curve perfectly, but it doesn't tell you what happens. Like why, all right, so if the coil is expanded all the way through here, how can the size change? Right, in other words, it's expanded here, it's expanded there, it's expanded there, it's Gaussian here, but there's no on-off switch. It isn't like expanded theta. It's continuous. So somehow the coil can accommodate this like changing condition with temperature. So the way it accommodates it is what's in that plot. Okay, so you have the coil, right? If I look deeper, it's 2. If I look big, it's BF is 5/3. So it's expanded and it's making little kind of beads, right? And as the temperature drops, those beads get larger, and the overall coil size drops. So it's accommodating it on different sizes because we had chi is going with n, right? So basically, the chi value changes with n. If you look at smaller parts of the chain, and a smaller chi smaller, you get more miscibility. That's kind of how it works. Right, so if you smaller things dissolve, let's see, chi goes with n, then the 1/2 minus chi changes as a function of n. Right, so that means the miscibility is different at different size scales. And the way this works is that the small size scales, you're going to start, say you have a perfectly expanded coil, right, ignoring the persistence part and whatever else happens out there. And then I'm going to use CST. I'm going to lower the temperature. Then all of a sudden it's going to go to -2. If I lower the temperature more, it's going to go to -2 here. But when it does that, this overall size shifts that way. So because it's made up of a random walk, but the random walk is made up of these big 2 things. It's kind of hard to draw it in a picture. But basically, this rate of gyration will shift that way. This cutoff point will shift that way until finally the whole thing will be just this Gaussian thing. There's a way to draw that, right? But I didn't do it to show how the RG changes. But okay, so that's what's going on, and he shows it. He's kind of you can see it in this plot. So anyway, you can see it in the linear plot. So basically, you got to draw the line and find that crossover point to get the Q value there, and then take 2 pi over that Q, then plot that radius, that size versus temperature, right? So find this point. So do log, may or may not be able to do this. If you can't do it, it's okay. So we got like the -5/3. It's going to go to -2. Just kind of move those lines around until you can find what that Q is. Right, then 2 pi over that Q. We call this thermal blob size. That's the term people usually use. You should be able to plot that versus temperature and that functionality is actually predicted in the notes. Let's see. The functionality for that guy is in, oops, I just had it here. Not here. It's in the notes later on. Anyway, you can just plot that. We'll go to the dependence of that later on. But basically, you can plot that number. You can see that it gets, as the temperature goes up, that number gets bigger. As the temperature drops, that number gets bigger. So as the phase separates, that thing eats up the whole coil. And then eventually, your coil size will be like that number at low temperature. It should go like that. Should match with the coil size. So the whole thing is 2. This is a mix 5/3 2. So you can see it in his data. It's in, I don't know how worthwhile this is, but you can see that. So it's kind of good enough to just see how that works. This -4, so there is a -4 out here, and there's a background that he shrouds it in. So like he never subtracts off this background. If you subtracted that off, you'd see there was a -4. What that is, like, it's probably, who knows what it is. I mean, it could be that you could say that if you get to even smaller sizes, it has like it collapses. So you have like a collapsed things inside a Gaussian, inside an expanded. This is the branched one. That one also works for. So there's a 5/3 in the branched, and it also has a 2. So you can get the transition between 2 and 5/3 at the 3 temperatures of the branched. And then he does it for the star, and it doesn't work for the star because of this correlations in it. So in fact, sometimes in stars you can see a peak here. Right? So stars won't work. The stars have, I mean, you can look at the stars if you want. Basically, you could take the 4 and kind of say it's got a 4, like they're a solid object in large sizes. Then kind of within that solid object is expanded coil, like this is the expanded coil one. I mean, so the stars don't work. That's kind of the bottom line. But you can look at the star one. I mean, he included it because it's easy to make, and industrial, they like it or something. But
so where exactly do you see the force? Because I'm struggling with seeing -4 power.
yeah, well, you can't see it. You'd have to subtract off that. There's a flat background here. Anyway, it's steeper than 2, right? And if you're steeper than 2, kind of the only other option is 4 here.
Can't be a 3, right?
Can't be a 3. And then if you subtract off this background, then you find out it goes to 4.
Okay.
So why it's not supposed to go to 4, it's supposed to go to 1, like the persistence unit. But it's for some reason it goes to 4. It's something they didn't talk about. And all they did was measure the rate of gyration. That's it. So there's a lot of information actually in these curves that he skipped over. Hopefully you can enjoy doing this. If not, don't worry about it. Like just, you know, but basically you can play around with Igor a little bit. You might find that it's useful to, I wanted to mention this other guy though. So that's it, I think, for that. For that, what is C star? Why is it important? Compare the shape. Like he shows a linear plot RG. It's supposed to be this other plot. Why did he do the linear dependence? Because he's an idiot. I mean, he hasn't studied polymers, and it becomes obvious, you know. Then the slope thing, find the transition. And then, all right, this one. So he claims this thing, and he measures the size dependence, but there's also just the temperature dependence, the Arrhenius behavior of the oil, right? Mm-hmm. And with the thing that he has, he's only getting the polymer contribution part from that intrinsic viscosity thing, because you've removed the solvent, you move the oil viscosity when you do that. It's the mixture minus the solvent. So the solvent dependence is gone. So the question is, if you have the Arrhenius parameters, what is the change from 25 to 90 for the oil itself? So his intrinsic goes by a factor of 2. It changes this the structural changes the viscosity by factor of 2. What does the Arrhenius change for the oil? Is it like 10? Then the 2 doesn't matter. Or is it like 0.1? So I gave you some numbers for the Arrhenius. You can calculate what the oil would have done just on its own, and then what would it do with, I mean, he says what it does with the polymer, So that's that thing. Yeah, you should be busy, I guess, with this. And then this one, this is just another way to do the same thing, but I just wanted you to look at that paper, but then just comment on the PEO. It's like, is that thing really going to work? Let's see, this one. Okay, so he says, like, he has polystyrene at the end. It phase separates when you cool it down. It's got a UCST. It phase separates just the same way. So he's got at high temperature, it mixes, and then he gets a network forming. He gets a high viscosity, and then when it cools down, it becomes, the polystyrene is immiscible. It pushes out, and the network falls apart. So he gets a low viscosity. So if it's in an oil, this does the same thing that the other guy did, but a lot more effectively. I know a network has a lot higher viscosity than just this expansion, contraction, Einstein thing. So anyway, but the problem is he's got this surrounded with tween, and then these chains are PEO. So all that stuff phase separates at 60. So you can't go to 90 because the whole system destroys itself at 60. So it's kind of funny. He doesn't mention that in the paper. Yeah, it's not going to work because the whole thing would fall apart. So he doesn't mention that. The idea is nifty and good idea, but basically it's got a couple, this flaw, So I wanted you to kind of conjecture on what happens to his viscosity. What happens to his viscosity when he goes up and that PEO phase separates out with an LCST instead of a UCST. He's got two critical things. He's got an LCST and a UCST, and they're fighting against each other. So anyway, but I thought this was a pretty good paper. Like, I like this paper. But it's simple. It's short. It's got the G prime, G double prime stuff that we talked about. So you can kind of glance at that if you want. The question is just kind of simple. You can see it's pretty simple. I mean, you by the tween, you get some cyclohexane and water. You don't even have to put it in a blender, you just shake it, and it'll self-assemble into these vesicles. And then I think you just bought this polymer, PEO with polystyrene at the end. And you just mix it up and heat it and stick it in the rheometer. He's doing, this is dynamic light scattering to get the hydrodynamic radius thing, and then he does that viscometry measurement to get the kind of the plateau modulus network or something. I just thought it was kind of an interesting paper. I was looking for things about coil expansion, and somehow this came up. And it's kind of this, they're addressing the same problem like thermal control of viscosity with polymers. So that's about it. So email me if you got questions. You should work on it. There might be a lot. I don't know. See what you think. And if it's too much, just I don't know. Everyone's got a good grade, so it doesn't matter much. So hopefully, I'd like to think that you could use the Igor program something like it. It's really useful for like scientific plotting, and you can program it and stuff too. So anyway,